Hi everyone, I'm going to work through lesson 4.3, same as if we would do it in class with the PowerPoints and such. And so section 4.3 is on logarithmic functions. And here are the concepts that we're going to cover. The first one that we're going to cover is converting between logarithmic and exponential forms. I can't emphasize how important this is. This is about half the battle of understanding logarithms, is understanding that it's just a different form of writing an exponential function in. So if you could switch back and forth between the log form and the exponential form, it's a huge benefit to you. So the definition of a log function is that x and b are positive real numbers such that b is not equal to 1. Then y equals log base b of x is called the log function, where y equals log base b of x is equivalent to b to the y equals x. So if we're looking at this, we're saying that, hold on, I'm having a hard time with my pen for some reason. So you'll notice that this has all the same parts in it that this does. So if we look at the different parts, if we could switch from this part to this part, that's the thing that I was saying is so important. So on this left side where it's got the logarithm part, you'll notice that you have a b. And you read this y equals log base b of x. So always emphasize base is the base. Okay, so in both of these, the b and the b are the base. We read this y equals log base b of x. And over here in exponential form, we already knew that this b is called the base. And so the base is always the base, whether it's log base something or whether we know it's the base because it's in the exponential, or in the exponential form. Then beyond that, when it's in log form, you have a number, or a variable in this case, that's with it. Over in the other form, that x is by itself. You notice here the y is by itself, and here the x is by itself. So in the log form, one of the numbers is by itself, in this case the y, and in the other form, the other one is alone. So I know it's a little bit hard with the variables, so let's look at it with some actual numbers in here. And again, these two mean exactly the same thing. A logarithm is the inverse of an exponential function. So on each of these, we want to be able to write these in exponential form. So if we're looking at this first one, you'll notice that this 4, whoops, I'm having problems with my pen for some reason. It keeps wanting to go to something different. So you'll notice that this 4 is the base. So we have 4 as our base in our exponential form. And remember, whatever was alone before isn't going to be alone anymore, and whatever was with the function is going to be alone now. So the 16 isn't going to be with the 4 anymore. The 16 is going to be on the other side, and the 2 that was alone is going to come over and join the 4. So 4 squared is 16, which of course we know is true. So, sorry, I had to click ahead on the slide. I'll get used to this. I haven't done this with a PowerPoint before. I've done it with other things, but not a PowerPoint. So the next problem is log base 5 of 0.2 equals -1. So this will make a lot more sense now that you can see the whole problem while I'm working it. So we have a base here of 5, and remember the base is the base. So that's going to be the base of our exponential function. Whatever was alone is going to come back and join that. So that's -1 goes with the 5. And what was with the 5 before is now going to be alone. So they just switch places. Before 0.2 was 5's buddy, and -1 was alone. Now -1 is over here with 5, and 0.2 is alone. So they switch places as far as which one is alone and which one is with the 5. So 5 to the -1 is 0.2. We know that's true because 5 to the -1 is the same as 1 over 5. And 1/5 is the same as 0.2. So that does give us a true statement. So the next thing that we're going to look at is log base 8 of 1 equals 0. 8's going to be our base. So 8. The 0 is going to come over and join it. And then the 1 is now going to be alone. So 8 to the 0 is 1, which is true. And same thing here. 23 is now our base. We're going to take that, the 0 is going to come over and join it as its power. And then that's going to equal 1. And 23 to the 0 is 1. Same as 8 to the 0 is 1. Anything to the 0 is 1. I apologize, I keep not clicking ahead on the slide. So that was log base 23 of 1 equals 0, and 23 was the base. 1 moved over, and 0 came to join it. So for examples 5 and 7, it says we want to write each of these in logarithmic form. And so we're going like the other way. Before we were starting with the logarithm and going to the exponential. Now we're going to start with the exponential and go to the log form. So in this case, we've got 2 to the 4th equals 16. Well, remember the base is the base. And in the log version, the base goes down here below the log. So log base 2. The 4 was with the 2, so he's going to be over here alone now. And the 16 is going to go over and join the 2. So log base 2 of 16 is 4, which means the exact same thing as 2 to the 4th equals 16. Just written differently, but they have the same relationship between the numbers. So this next one, I'm going to start with the logs, trying to go to the log form. The base is still the base, so it's going to be down here. The 3 is now going to come join the 27, and the 1/3 is going to go over here and be by himself. So log base 27 of 3 equals 1/3, because 27 to the 1/3 equals 3. And as we do these, if you want to give it a shot, of course with it being a video, you can pause it and try them on your own and then see how you did. Alright, so on this we have log. Our base is 1/4. -2 is going to be over here alone now, and the 16 is going to come over here and join the 1/4. So log base 1/4 of 16 is -2. So our next thing that we're going to cover as far as concepts is evaluating log expressions. And so here are our logarithmic expressions. We're going to start with log base 12 of 144. And what we want to do with this is we're going to switch the form. So you'll notice that we don't have this equal to anything. One little hint that you can do is make this equal to something. And since you don't know what that something is, make that x. That way, you'll notice now we have all the pieces that we need to switch the form. So if we take 12 as our base, x is going to come over here and join the 12, and that's supposed to equal 144. So we're trying to guess or figure out 12 to what power is 144. Well, of course, 12 squared is 144, so x must be 2, which means that, take this x here, and I won't do this every time, but that means log base 12 of 144 is 2. So that's what we were looking for. We were looking for that number that you could take 12 to that power and get 144. Again, think of it, it's a similar relationship to like a square and a square root, where they undo each other. You know, you could take the square root of 25 and you get 5. When you look at that, you probably think to yourself, what times itself would get me 25? In this case, I'm thinking 12 to what power would get me 144. Very similar thought process. In this one, we have 64 and 8. Again, I don't have it equal to anything. That's a little awkward because we like to have all the pieces when we switch the form. So I'm just going to make it equal x because I don't know what that is. So 64 to the x equals 8. Now that's a little bit more difficult because we're going, you know, it's not saying 8 to the power equals 64. It's saying 64 to a power. So when we look at this, you're saying, well, what could I take 64 to a power of to get a smaller number? That doesn't seem to make sense. Well, if you remember, we know that the square root of 64 equals 8, speaking of square roots. So how could I write a square root as a power? Well, it may have been a while since you've seen this, but a square root can be written as a power of 1/2. And so 64 to the 1/2 power equals 8. So if you have a square root of a number, we'll just say n, that's the same as n to the 1/2. If you had a cube root of a number, that would be the same thing as the number to the 1/3, and so on. So you can always use that relationship. But in this case, the answer that we were looking for, log base 64 of 8 is x, so an x has to be 1/2. So log base 64 of 8 is equal to 1/2. Here we've got, let's set it equal to x again. So 3 to the x, 3 is our base. X is going to move over with the 3, so 3 to the x equals 1/27. Now if that said 3 to the x equals 27, that would be easier because we know 3 cubed is 27. So how can we take care of this situation where we want the 27 on the bottom? Well, remember, if we take to a negative power, then that'll flip it. So if I do 3 to the -3rd, that should equal 1/27, because 3 to the -3rd would be 1/3 to the 3rd, and 3 to the 3rd is 27. Let me write that. So like if I did 3 to the -3rd, that would be 1/3 to the 3rd, which would be 1/27. So we're going to talk about two very specific logarithmic functions now. There's two different logarithmic functions that we write in a shortened version. If you ever see log base, or log with no base at all, like this one, then, oh, my pen, ugh. Okay, so if you see it written with no base like this one, it's not that they forgot it, and it's not that it doesn't have one. It has to have a base. It's just that we use log base 10 a lot. So it's kind of like when you write a square root. Again, square roots and logs aren't the same thing. I'm just using them as kind of a reference. But when we do a square root of 25, we don't write the 2 outside. We could, but we usually don't. And that's because we do square roots so often that at some point somebody said, oh my gosh, if we mean a square root, can we just, if we're going to do a square root, can we just leave the 2 off and everybody knows it's a square root so that we don't have to keep writing that? And that's basically the same thing that's happened here. Whether it was a matter of writing, or it may have been in a long time ago, it might have been a case of typesetting. Remember in old books they used to have to take every little bit and put it into the press. And so, you know, not having to put a 10 in there, if it was repeated a lot of times, would save a lot of effort. And so if they don't have a 10 here, or a number here, then it means it's 10. Same thing with this. We also do log base e a lot. And so to differentiate these but still not have to write the base every time, this is called a natural log. And so they do a lnx. So if you ever see anything that has no base, a log would be a base 10, and an ln would be a natural log, which is base e. So if we're going to evaluate these expressions, basically that means we want to write them, we want to figure out what they equal, which means we're going to have to write them in that other version so that we can kind of get a handle on what they are. So in this case, we've got log base 10, or log of 100. It doesn't have a base. If it doesn't have a base, we know that's a 10. And it's not equal to anything, so let's make it equal to something. So this is going to be 10 to the x equals 100. Well, we know 10 squared equals 100, so x must equal 2. 10 squared would be 100. So in this case, log base 100, or log of 100 rather, it'd be a base 10, equals 2. over here, again, we don't have a base, and it's an log log, so we're going to do a base 10, and that's going to be equal to some unknown x. So 10 to what power would get us 0.0001? Well, it's going to have to be a negative because it's smaller than our base. So what is the negative? Well, the decimal's been moved. The decimal's been moved to the left. So 10 to what power would get us that? So is it -3? Again, I'm just kind of playing around with this so you can see how I do it. Is it -3? Well, 10 to the -3rd would be 1 over 10 to the 3rd, and that would only be 1 over 1,000. And we actually want to be tenths, hundredths, thousandths. We want to be all the way to the 10,000ths place. So it's not -3 because there's 3 zeros. It's actually -4 because we have to get around the 1 before we come back. So it's not 10 to the -3. It's actually 10 to the -4. Because 10 to the -4 would be 1 over 10 to the 4th, which would be 1 over, with 4 zeros, and that's 1/10,000th. And if you count the digits here, we have tenths, hundredths, thousandths, 10,000ths. So this is 1/10,000th, which is the same. So in this case, x would have to be, don't forget to write your final answer, x would have to be -4. We're trying to find that logarithm is that exponent. So we're trying to find that exponent, which was -4. Okay, on this next one then, we don't have a base here, so we're going to write it as log base e of e to the -3. Now this looks awful at first, but it's actually going to be pretty easy to figure out once we get it all written out. So I'm going to put that base in there. I'm going to set it equal to x, and now switch our forms. E is our base. X is now going to come over and join e, and then this bit that was the raised part on the log is going to go over here by itself, e to the -3, and now you can see, well, I have e to the x equals e to the -3. Well, if these are going to be equivalent, the x and the -3 must be the same. So x must be -3. So natural log of e to the -3 is just -3. This one, again, put it in the form that we like. Don't try to work with it like this, at least at first. You probably can later. But at first, write it in the form we want. So we don't want a natural log. We want an log log with our base e. So the natural log means base e. So I'm going to put that e down there of e to the 10th. And I'm going to have it equal to something so that I can switch forms. So e to the x equals e to the 10th. And that's exactly like we had over here. So you can kind of see this is going to be a property eventually that we're going to try to just remember and use. That if you take natural log of e to a power, it's just equal to that power. So in this case, x is 10. So natural log of e to the 10th is just 10. So now in these it says to use your calculator to find the approximate value. And then round the answer to 4 decimal places. So give me just a second. I'm going to open up a calculator here. Okay, so on the graphing calculators, you can do logarithms. There's a log button right here. And all we have to do is type in log and then the number. Now the only thing is remember that log, when there's no base, means base 10. So I can't push this log button if it's any other base. But this problem has log base. There's no base there, so that means it's base 10 and then a 43. So if we just hit the log button, type in 43, we can close the parentheses since it's the only thing we probably don't really have to. But if we hit equals, we get 1.677, so on. So if we, or 6334, I don't know where I got 7 from. So if we were to round this to 4 decimal spots, 1.6335, because the 4 would round up to 5. Okay, I'm going to have to get a little creative so the calculator's not in the way on these. But if I clear this out now, and if I want to do the approximation of log of 200, again, this only works, remember, if there's no base here or if it's a base 10. So I'm going to do log of 200, and that ends up being 2. They said to take it to 4 decimal places. So we're going to do 2.3010. So 0 is followed by a 2, so it doesn't have to be rounded up. Okay, the next one that we have, let's slide this over. Oh, that's not what I meant to do. There we go. So slide this over and we'll do log of 0.074. And that comes out to be approximately negative 1.1308. So if we round that properly, 13076 would round up to 13008. The next one we have, you'll notice, is a natural log. Your calculator will also do natural logs. So the natural log of 200 is, here's the natural log button, 200. Close that up, and you've got approximately 5.2983. And then our last one is natural log of 1.05. Natural log 1. It's actually 0.005. And you notice this one came out with a scientific notation. So you could either write it, it's up to you, you could either write it as approximately 4.9875 times 10 to the negative third, or if you want to actually write it in straight decimal form, that means we have to shift the decimal to the left 3 places, so around the 4 and then 2 more spots. So we were here, and now we went back 1, 2, 3 spots. And if we're following the rules of only rounding to 4 decimal spots, technically 4 decimal spots for this would be where the 9 is, so it's going to be 0.0050 because the 9 is going to round up, but that's going to make the 4 round up. So 0.0050. I don't really mind how you do that, but you know, Connect Math sometimes gets a little picky about that. So now we're going to apply the basic properties of logarithms. And these are some things that hold true no matter what. We know that b to the 0 is always 1. So if you have a base of anything and it's supposed to equal 0, I'm sorry, a base of anything with 1, then that's going to equal 0. Again, if you switch forms, if you're looking at this and you're trying to reconcile it and you can't necessarily remember the property, you can always switch the form. So whatever the base is to the 0 power, put the 0 with the b, equals 1, we know that's always true, that anything to the 0 power is 1. Also, if you have a base of b and you raise it to a first power, it's always going to equal itself. So log base b of 1 is always going to be 0 no matter what that base is. Log base b with this part as the same number, this is called the argument, these are the same number, then you're going to have this equal to 1. In this case, log base b of b to the x equals x. That's kind of like the natural log one that we were doing. If you take b to the x, so here's your base, here's what it equals, but then that's supposed to equal b to the x. Well, that makes sense. Of course, log base b of b to the x is going to equal x because b to the x equals b to the x. And then this one is in exponential form. Actually, it looks a little weird because it's got this logarithm up here. But this is actually in log form. So if we take it, or in exponential form, so if we put it in log form, that'd be log base b. Here's our base is now our log base. the x is going to come over here and join it, and this exponent is now going to be alone on the other side. And you can see that, of course, b to the log base b of x is x, because log base b of x is equal to log base b of x. So those are just some things that always hold true. You can always kind of reinvent those if you need to when the time arises. But if you remember them, it just saves you time. So on these, we want to simplify these expressions. Boy, they got a lot of them here. We'll go ahead and go through all of them, though, because we're not constricted by our class time like we normally are. So we'll go ahead and simplify each of these. I would always make sure that you set it equal to x. So we had a property for this, but let's, and you may remember the property, but let's just double check it. So they're saying 19 to the x is supposed to equal 19. Well, what's that x have to be? It has to be a 1. So log base 19 of 19 is just 1. Let's use the eraser, make that a little bit neater. So that was the property log base b of b equals 1. So that was one of our properties. And that's the example of that. So here, if we set this equal to x, remember this is a base 10, and there's nothing there. So 10 to the x equals 10. Well, the x would have to be 1. So this is a situation of, if you take something to a base and then have the same argument here, it's always going to equal 1. So this was an example of log base b. Oh, that's the one we already wrote. So it's the same one that we already did. Log base b of b is 1. Same thing here. Remember, natural log e means log base e of e. And we already know that if you have a log and a base with the same argument, that this is just going to equal 1. Because e to the x is supposed to equal e. So e would be raised to the first power. So now on these, we've got 273 to the x power equals 1. Well, the only way to get 273 with a power to equal 1 is if that power is 0. So log base 273 of 1 is 0. And that's an example of log base b of 1 always has to equal 0. So we can use that again here. Log base b of 1, or log base 1/8 of 1, would have to equal 0. And that is because 1/8 to the 0 equals 1. Here we've got log base 30 of 3 to the 10th, and we want to know what that equals. So we'll set it equal to x. 30 to the x equals 30 to the 10th. Well, that x would have to be 10. So we'll write that in, and then we'll write which of those properties that was. So x would have to equal 10. And that was log base b of b to the x has to equal x. So there's an example of that one that we saw a little bit ago. Here I'm going to rewrite it with log base e of e to the negative 12. That's the same property. I've got the same base here as I do here, so that must mean that this equals negative 12. You don't have to remember the properties again, but it does save you time if you do remember them. So here I've got a base with an exponent, so I'm going to switch it into log form. This is equal to x. So x, I'm sorry, I should have started with the log. So if we do log base 10 of x, remember this comes over now with the 10, and the exponent is going to be by itself on the other side, log of 14, which means log base 10 of 14. So the x must be 14. And that's an example of the property b to the log of x is going to equal just x. And this is the same thing. We have b to the log of, and I should say log base b of x here. So this is 8 log base 8 of 5. This is going to have to equal 5. Because 8, if I write this in log form, log base 8 of 5, this is our base I'm putting down here. This 5 comes over with it, and then that's supposed to equal the exponent. Well, the exponent is log base 8 of 5. Okay, so there's our answers for those, all those expressions. And now we're going to graph some log functions, and then we're going to do some application problems. So if we're going to try to graph an exponential function, what is that going to look like? So this is there's a little trick to doing these that you need to know, and that is that in order to get the table, we actually have to start with the y values. So what we're going to do is we're going to rewrite this in exponential form. So remember, our base is our base. So we have 3. That's going to be to the y power. And then that's supposed to equal x. We're just switching forms again. This one's kind of backwards. Let me write it the other way. So we always saw it this way before. I'll write it up here so we have room. So think of it as log base 3 of x equals y. Remember, 3 is going to be our base, and then y is going to come over and be our power, and then the x is now going to be alone. Well, the way that it's written here, it looks like it would be a whole lot easier to pick y values and figure out what the x is, and that's true. So what we're going to do is we're going to pick some positives and negatives for y, and we're going to then figure out what the x's are. But we have to make sure we put it in the table in the right direction. So we're picking y's. So we're going to pick, say, -2, -1, 0, 1, 2, 3, 4. So if I put in, we'll start with easy stuff. So 3 to the 0 would just be 1. So log base 3 of 1 would be 0. If I put in a 1, that's just going to get me 3. If I put in a 2, 3 squared is 9. If I put in a 3, 3 to the 3rd is 27. And then 3 to the 4th is going to be 81. Now if I go the other direction, remember 3 to the -1, I'll write this one off here. So 3 to the -1 is 1 over 3 to the 1. So that's 1/3. And same thing with -2, that would be 1 over 3 squared. Because this would be 3 to the -2. And so this would be 1/9. So you can see these are getting small fairly quickly as we progress upward. These are getting large very quickly as we progress downward. So now we want to graph these, and remember, this is your x and this is your y. Just because we pick the y's first doesn't mean it gets graphed first. So our y is 1/9, so barely off of the y-axis, and then we're going to be down at -2, so it's going to be, just barely off the x-axis. And then 1/3, -1 is going to be, just a little bit more off the x-axis, but not very much. And then we have 1, 0, and then we have 3, 1, then we have 9, 2, and then we're off of the graph that they've given us. So this would graph something like this. And you'll notice it sort of looks like an exponential. This is supposed to come in closer and closer to the y-axis as you go down. Hard to draw with the tablet. But you'll notice this looks like an exponential, but it's turned on its side. So if you could flip that and bring it, rotate it around here to the left, it would look like an exponential function. And that's exactly because the exponential and the log are inverses of each other. So now just some things to point out. The graphs of exponential and logarithmic functions, a logarithm is going to be like we just did here. It's going to have the point 1, 0 every time. So it mentions that here. But it's going to have the, hold on, let me get my pen going again. So it's going to have the 1, 0 every time. That's here. Okay. And then, so that's right there. And then the other one, the exponential, is always going to have 0, 1. Because whenever you put a 0 in for x, you're going to get a 1 back for y. So this graph will always have 0, 1 on it. The domains and ranges will be switched. The domain of the exponential will be from negative infinity to infinity. Again, that's the blue one. So you see that the domain of the blue one is from negative infinity to infinity, while the range of the other one is from negative infinity to infinity. Here the range is from 0 to infinity, so you can't go below 0, and then it goes up. On the other one, the domain does that. The domain can't go below 0. You can't go any further to the left than 0. I mean, you won't ever actually get to 0. It stays to a little bit to the right of 0, but then it goes all the way to infinity the other direction. So the lowest the range can go, or the domain can go, is 0, but not including 0, but then it can go forever to the right. And the exponential goes the opposite of that. It has its range is that. It can't go below 0, but then it goes up forever. So just some little details to point out on the different graphs. So on this one, it says we want to use transformations to graph the function. And so we're going to think about an original function, just a log base 2 of x, and then we're going to transform it. Hold on, I don't know why my graph, there we go. And then we're going to transform it. So we're going to start with a regular base 2 of x, because that's our base that we have. But then we're going to shift it by using this +1 and this +2. But first we want to graph the original. So we're going to do the same procedure that we did before. We're going to start with our table. So here's our x and our y. We're going to think of our original base 2 function. So we're going to think of y equals log base 2 of x. But then we're going to switch the form. So we're going to make it 2 to the y equals x. So 2 is our base, then y partners with it now, and x gets to be alone. So I'm going to pick y values. So I'm going to do -2, -1, 0, 1, 2. And 2 to the -2 would be 1/4. 2 to the -1, if I put that in here for, remember these are our y's, so if I put that in for y here, 2 to the -1 would be 1/2. 2 to the 0 would be 1. So again, we're putting the 0 in here. So 2 to the 0 is 1. If I put a 1 in there, 2 to the first is just 2. And then this one I would do 2 to the second. So that would give me 4. So these are the points that I want to graph initially. Then I'm going to go and I'm going to do the shift on it after I get those done. So I have 1/4 -2, very close to the y-axis. Then I have 1/2 -1. I have that 0.10 that I have in all non-shifted exponential graphs. And then I have 2, 1. And then I have 4, 2. So here's our original. I'm going to do it kind of dotted because it's not our final answer. So here's our original graph. But now I want to take every point on this graph and I want to shift it according to this. So this is like, I don't know why they put 1 plus x. It's the same as x plus 1. So when we do a +1 with the x, remember, that shifts it left 1. So we're going to go left 1. And then the 2 plus 2 means we're going to go up 2. So let me get a different color so we can differentiate it. So this will be our final answer. We want to take all of these points and we want to go left 1, up 2. So if I take this point and I go left 1, I'm doing the very first point, starting here. I'm going to go left 1, up 2, and that would be here. Okay, so I moved it from here I moved it left 1 up 2. And then I'm going to do that with all the points. So the next point I'm going to do is this one. I'm going to move it left 1 up 2. This point I'm going to move it left 1, working on this point, left 1 up 2 would be there. Now I'm working on the point 2, 1. I'm going to move that left 1 up 2, which would put it here. And then my final point is this one, and I'm going to move it left 1 up 2, would put it here. And then we have this new line that we can't cross. So instead of not being able to cross the y-axis, we can't cross the x equals -1 line. It's going to hug it, but it's not going to actually ever cross it. So it's going to look something like that. Skipped a bit here. So it's all supposed to be nicely connected. So now we have this log base 2 of x plus 3 that they've graphed for us. And they want us to determine the domain, the range in interval notation, and then the vertical asymptote. So in this case, let's start with the vertical asymptote because that's pretty easy stuff. So that's basically what is it hugging. So if you notice, this is going along the x equals -3. And it's kind of hard. I know the blue line looks like it crosses the x equals -3, but it really doesn't. It just gets closer and closer to where you can't differentiate visually. So this line is x equals -3, and that's exactly because we shifted it left 3. So the vertical asymptote is x equals -3, and then the domain is what can it go from left to right? Well, it stops at -3, so the domain starts at -3, but it can't cross it. And then it goes to infinity. So it starts here and goes that way. That's our domain. So it starts at -3 and goes to infinity. The range goes as low as, it just keeps getting lower and lower and lower. And then this, even though it doesn't go up super fast after this, it does keep increasing, as we go. It keeps getting higher and higher. So the range is from -infinity to infinity, which is what we talked about on that other slide, that's how they behave. So here we're to give the domain and range again. So the domain on this one, it looks like it's bounded here by the x equals 0. So right here, the y-axis is the vertical asymptote, which is technically x equals 0. The domain, how much can it go left and right? Well, it goes up to but doesn't include 0, and then it goes to infinity to the right. So again, we're looking like this way. It bumps up against that x equals 0 on the left side, but on the right it's unbounded. And then for the y, it's going to go from -infinity to infinity. So this is your domain, and this is your range. And then the last thing that we're going to look at is some applications. So our example problem, or our application problem, is about the absolute magnitude of a star. The absolute magnitude by definition of a star is the variable's m, and it's the apparent magnitude m a star would have if it were placed 10 parsecs from Earth. I don't know what all of this, I know basically what it means, but I don't know very much about this. But I don't need to know very much about it. I just need to be able to use the formula that they're giving me. So it says the lower value of the magnitude, the brighter the star. So our sun has an apparent magnitude of -26.74. The brightest star in our night sky is Sirius, the dog star, with an apparent magnitude of -1.44. The sun appears so bright because it is very close, astronomically speaking. So again, remember, the lower the value, it says, the lower the value, the brighter the star is. So Sirius being negative 1.44 is much, much brighter than our sun. The sun appears so bright because it's close. So the reason that the sun appears so bright is because it's close. If we were to get as close to Sirius as we are to our sun, it would, despite the fact of, the burning up part and all of that, it would be very, very, very bright, much, much brighter than our sun. It isn't because it's so far away, like it isn't to us visually because it's so far away. So anyway, the formula that they give here relates a star's absolute magnitude, apparent magnitude, and its distance from Earth in parsecs. So we're going to take that and answer the following question. So it says that we want to find if Sirius is 2.637 parsecs from Earth and the sun is 4.887 times 10 to the negative 6 parsecs from Earth, what's the absolute magnitude of each star? So remember, we had the apparent magnitude and the absolute magnitude. So here's the formula that we had, but we also have to go back and get the numbers from the prior slide, and we'll get those filled in. So the apparent magnitude of the sun was negative 26.74, and of Sirius was negative 1.44. So we can use those in our formula when we do. So now we'll do Sirius first. So Sirius, the magnitude is m. Well, that's silly. Put that number in there. The magnitude is m, which is its apparent magnitude, which is negative 1.44. So I'm just putting that into this formula up here. And then I'm going to subtract 5 log, and then the distance is 2.637 over 10. And then we're just going to type this into the calculator. So we're literally just going to take that and take our calculator and type it in. So we're going to do negative 1.44 minus 5 log parentheses, this one gives a parentheses, see it already has a parentheses, 2.637 divided by 10, then close the parentheses, and we get 1.45544. Again, I don't really have to know much about that formula. I just have to be able to plug the numbers in where they belong. So it's 1.45. We'll just leave it there because that's how they rounded the apparent magnitude. So we'll say it's got a absolute magnitude of 1.45. And then our sun, we're going to do the same thing. So its absolute magnitude, the big M, would be negative 26.74 was what they gave us for the little m. That was the apparent magnitude, minus 5 times log of the distance for the sun is 4.887 times 10 to the negative 6 over 10. So then we're going to type that into the calculator. Negative 0.74 minus 5 log, and I think I'll use a fraction just to make sure I don't mess anything up. So 4.887 times 10 to the power of negative 6, little be real careful getting it in here, but it's very doable. And then we're going to put in the 10 on the bottom. And then we're going to arrow over and get our parentheses and hit equals. So the absolute magnitude of our sun is approximately 4.81. And again, you're like, why is the sun a bigger number? Remember, with the magnitudes, the smaller the number, the brighter it is. So the absolute magnitude of the sun has a bigger number, which means it's less bright, because Sirius has a smaller number. That means it's brighter. So this is basically, if we put them side by side instead of looking at them from Earth, how would they compare? So Sirius is brighter than the Earth. And that is it for what we were going to cover in 4.3. Hope everybody has a great weekend, and we'll see you back on Monday.